Hi everyone, let's solve today's daily challenge, that is invert binary tree. In this question, we are given the root of a binary tree and we have to invert the tree and return its root. Right, so let's see what inverting a binary tree means. So as you can see in this example, this is the first example I've taken here. So if you see in this, inverting simply means that you just swap the children of a particular node. So if we start from the root, originally 2 was its left child and 7 was its right child. So what did you do? You swap these two, right? Similarly, if you see 2, right? This is another node, and if you see its children, you just swap them, right? So in the resultant tree, you will get 3 and 1. And similarly for 7, 6 and 9 were the 6 was left child, 9 was the right child. Now they have been swapped. So 9 has become the left child and 6 has become the right child. So that is what inverting the binary tree means, right? That is, you just take a node and you just check whether it has children or not. If it has, then you need to swap them. So it's a very easy question, right? So if you see, can we do it through recursion? Yes, we can do. Why? Because all we are doing is we are just considering a particular node and we are considering its both children, right? So if this node is not null, that means it has some children, whether even if it's null, right? Even like for example, if you see for 1, it is null and null. Right, so if there will be one recursion call for this one also, so as there are null and null, these will get swapped, although that won't affect our result, but still here only up till all the leaf nodes there will be recursion calls. Okay, so you can see simply for each and every node you just have to swap their children, right? So that is the only logic of this problem. So let's solve it. So what we are saying is we can do this through recursion, right? So what will be the base condition? The base condition is nothing but if the root is null, you don't have to do anything, right? So that means if we don't have to do anything, we'll simply check if root is not null, right? If root is not null, then do something, then do the inversion, right? So when the root is not null, what are we saying? We have to swap these children, right? So what we'll do, we will simply say swap the left and the right of this tree, right? So this is done, right? We will be starting from this node, right? That is the root node. So for this, we swap these. We swap 2 and 7, so we will get 7 and 2. But now 7 has its children as 6 and 9 only. So that will give us the wrong result. We also have to call it for 7 and as well as for 2, right? So whatever children you have to recursively call this function for them also. So we'll say invert tree, and what will be passing? We'll be passing the left child as well as the right child, right? And after doing all of this, what we should return? We should simply return the root, right? We'll simply return the root of this particular tree. Now, if you see the time complexity will be big O of n. Why? Because let's say this tree was a skewed tree, right? That is 4, 7, 9. It was something like this. So we have 3 nodes, right? And they all are, connected through left children only. So that is a skew tree. So in that case, we'll be getting O of n complexity. So overall, the complexity will be O of n. Otherwise, for balanced binary trees, it will be O of log n. Similarly, for space complexity, we will be using a recursion stack here, right? That will also, if the tree is skewed, so in the worst case, we'll be having, all the nodes of that particular tree inside of the recursion stack. So that is why also the space complexity becomes O of n. Okay, let's also run it. Okay, so it's accepted, it's submitted. So that is how you have to solve this question.